So it's 14:45 UK time. Can you hear me?
Yes.
Giovanni, can you hear me?
Yes.
Okay.
Loud and clear.
Okay, so perfect. So it's my great pleasure to invite you to the final tutorial for today, given by Siamak Mehrkanoon. Hopefully I pronounced him correctly. And he is an assistant professor in the Department of Data Science and Fluid Engineering in Maastricht University. I don't want to go into details of his biography because there is a link to his homepage that you can find more details about him and also about his research, his presentation, his article and preparation. I just want to mention that he is a good example of young generation. He did his PhD in 2015 and in Belgium, and he did postdoc in several good places in China and in Canada. And today he is going to talk about, in fact, my favorite topic. It's called deep learning. And just a couple of remarks that deep learning changed landscape of machine learning, artificial intelligence for the last 8 years. Everybody knows this. And now you have majority of conferences that you just hear always only deep learning. Okay, so analyze this. And from one hand, it's a very simple mathematical construction. From another hand, you don't have really understanding why it's so good. And it's in many cases, it just contradicts all our intuition when, for example, you have network with a billion parameters and you have only 1,020 examples. According to our just philosophy, we have to, of course, overfeed all this data, but it's never happened almost. So there is a lot of mystery in this simple mathematical construction called deep learning. But before deep learning, of course, one of the most popular topics was, as I remember, it was support vector machine, kernel method, and all this one. And in this talk, we are promised to not only explain us what is a deep learning, but also explain connection with the kernel method and probably support vector machine, which is personally, I will be very interesting to learn. So I don't want to waste your time. So I want to ask Siamak to present his talk. Okay.
Thank you, Alexander. First, I want to test it whether you can hear me.
Yeah.
Perfect. So thank you for the very nice introduction. So indeed, the topic of today would be about deep learning and artificial neural networks and kernel-based models. So these are the two powerful framework in these deep learning scenarios. So I will just jump into the outlines. So it would be introduction to deep learning, and I will next talk about feed-forward neural nets, regularizations techniques that are used, and some of the architectures that are well known in this framework, like convolutional neural networks, recurrent neural networks, and GANs. And then I will talk about deep kernel-based models and connections to artificial neural networks. And at the end, if I had the time, I would explain something about domain adaptation. And we will go through some of the models from shallow to deep models that are used in this field. So as in general, artificial intelligence is any technique that enables computers to mimic human behavior. And a subset of that artificial intelligence could be machine learning, which is the ability to learn without explicitly being programmed. And a subclass of machine learning is referred to as deep learning, which the aim is to learn the underlying features in an end-to-end fashion. And it could be based on neural networks or kernel-based models. So currently, deep learning is doing a great job in many fields, and this is thanks to the fact that we have so many data, and also there are several softwares available, and also computer capacities are increasing. So thanks to these three things, we are dealing with deep learning methods that are really applicable in many fields. So a brief history of neural networks. This is not something that is new. In fact, it has been there for a while. So in 1942, it was Mehrkanoon and Pitts that they proposed a mathematical model for a neuron. And then we have a perceptron learning, which was introduced 1958. And then we have this backpropagation neural networks, which was 1986. Was introduced. That was the time that it was booming for neural networks as a universal approximators. But soon they realized that yes, there are some problems. They cannot scale these neural networks. So that means they cannot go very deep. Also, there was this vanishing gradient problem, and also there are many local minima problem, and that's why Vapnik in 1992 introduced a framework based on kernel models called support vector machines classifier, which the advantage of this framework compared to the existing neural networks approach was the fact that it was a convex optimization. So you would get a solution, a unique solution in the dual, and it has been used successfully in many applications, and still it's a successful method, but is in a different category. So many researchers, many scientists, in fact, they have been focusing from 1992 till let's say 2006-10. They have been focusing on support vector machines. But among some of these researchers, they kept working on artificial neural networks, and some of them are like Hinton or Benjiu that they were working for instance, for deep link networks or stack autoencoders, where explicitly these two last frameworks that I just mentioned, they were like a starting process for getting to know about this deep learning, how we can scale them, how we can have more than 3 layers, let's say 5 to 10 layers, how we can train them, and different techniques. And so it started, from 2006 or 2010, it started to, this deep learning framework started to boom. So it has many applications in traffic flow prediction, weather forecasting, logistics, neuroscience, medical image analysis, just name it. There are several applications and are increasingly every day. So let's start with the first one, the first simple architecture, which was perceptron, which was 1950s. It was just one neuron where you have the input. These are the variables of the first input, let's say. You multiply by weights and you sum it up, and you apply a threshold, then you get the output. So this is a simplified version of the actual neuron in the brain, and there are other variants of this modeling, but this is the thing. This is something that it has been working, at least from a machine learning point of view. So this activation function that is applied here has a good role. So the importance of this nonlinear activation function is the following: that if you, as you see in the left figure, if you don't have any activation function, the decision boundary would be a line. I mean, in the case that for the case that we are dealing with classification problem with two classes, but once we apply the nonlinearity, then the nonlinear activation function, then we can approximate nonlinear decision boundaries. There are several activation functions that can be used. There are Zigmuth function, or hyperbolic tangent, or rectified linear unit ReLU, and there are so many other variants that are based on ReLU. So this ReLU is a bit more recent than the other two. So these are range of activation functions that normally are used in neural networks. So once we design the architecture, that means we have the input, and we have to multiply by weights, sum it up, activation function, and then we apply the threshold. We go to the output. So the question is, how do we learn the weights? Because if someone gives us the weights already, a good weight, then the problem is done, because we just have to feed the data to the network and we reach the output. So the question is, how do we learn the weights? And for doing that, we have to define something called the cost function, or objective function, or loss function. And that is nothing but the difference, let's say, between the ground truth and the model prediction. So we want the difference to be as small as possible for all samples, training samples that we have. And this is referred to as cost function. So what we aim at is minimizing this cost function. And by minimizing this cost function, in fact, we would like to learn the weights that corresponds to the minimum of this cost function. The technique that has been used for doing so is called gradient descent. Probably most of you already know it. So then the intuition is the following: that suppose we are on top of a mountain, and we have zero visibility, and we would like to reach to this lake which is down there. And the best way to do that is to probably check around you and see where the direction of the descent is, and then go in that direction. So that's the intuition of gradient descent and how it works. But what is important is what would be the step size that you would take. If you take your step size too large, then it would be overshooting. That means you will never converge to that lake. And if you take it too small, then it will take a lot of time to converge to that lake. So this step size sometimes is also called learning rate in different optimization routines that exist. They are also referred to as the learning rate. So this figure shows that depending on where you start, you could end up with different points at the end. And this is again due to the non-convexity of the cost function that is involved in artificial neural networks. So if you start from here, this point, you would end up in here, and the other way around. If you start somewhere else, you would end up with something that is not seen before. And the difference between the two, there has been some studies that as the network is for deep networks, the difference between these two endpoints would not be that much high. So the difference is small. So that's, but still there is this non-convexity there, and this is not, we cannot avoid it. So if we want to summarize the gradient descent, so we take the gradient, we do the forward pass, and then we take the gradient of the cost function with respect to the parameters, model parameters that we want to optimize, and we multiply by minus sign here, and then minus eta, minus sign because we want to go down. Eta is the step size that we choose, and then based on this, we would update the weights. So by repeating this process, the weights of the network gets updated, and hopefully after some iterations, it would converge to something that we would like. So a simple model, well, not simple model, a model that's called logistic regression model also can be viewed from this simple architecture, as you see here. So we have the input, we multiply by weights, sum it up, we apply sigmoid function, and then we have a quantizer, a thresholding, which leads us to the output. And the question is how we can learn the weights again, and therefore we have to design a loss function that can be minimized, and then we need a learning algorithm, which by now we know that we can use the gradient descent to learn these weights. So we know all these things, and now, I mean, there have been studies that they show that this loss function can be used for logistic regression, which is obtained, well, I did not explain it in details, is obtained by taking the maximum, the likelihood, and then maximizing that likelihood, and then taking the log. And then since we want to minimize, then we multiply by minus. So we will get this loss function. So we can just minimize this loss function by means of this gradient descent, and therefore we would get the optimal W. So that was just to show that this logistic regression also can be viewed from this simple artificial neural network architecture that is shown here. Sometimes, well, often is good to use a regularization term because you would like to avoid overfitting. We don't want to follow the noise, but we want to really learn the underlying function that generates the data. So therefore, having a regularization term is important in machine learning and also deep learning. So yeah, people have been trying different regularization term. One of them is the L2 norm, so imposing L2 norm on the weights. These have the effect that it will lead to a better solution than not having that. So yeah, so that was about yeah, perceptron and a logistic relation that can be viewed as simple architecture. We can also extend it to having more than one neuron, because so far we have been just dealing with one neuron, which is connected to the input, but we can have multiple neurons and also multiple hidden layers. So therefore we can make it, then we can make the network deeper. And also there would be different architecture that we will discuss later that yeah, deal with different things like images and these things. So yeah, the problem is the more number of hidden layers, the better in theory, but in practice, deeper neural networks would need a lot of label data and could not be trained easily because of that vanishing gradient problem. And of course, there is this local minima that existed. So yeah, as I said before, because of these problems, there are powerful methods based on supervector machines or Gaussian process or least square supervector machines have been introduced to overcome these issues. But due to recent advancement in the field, that means we have more data, label data, we have a lot of yeah, a lot of companies are behind this deep learning. So that means there are many softwares available. So the whole community is excited and they are yeah, really pushing this framework forward. So there have been somehow a battle between the two frameworks of vector machines and artificial neural networks. Which one is better? Yeah, each one. I mean, each one has its own advantage. So support vector machines is convex, but it cannot learn the features. So yeah, at least from a classical supervector machine, it cannot learn any features or new representation of the data. But yeah, artificial neural networks, let's say CNN framework and these things, they can learn the underlying, I mean, new feature representations, and that is good. But both frameworks are quite good, and they're performing very good in different applications. So these are the three reasons that, again, these artificial neural networks have been emerged. Is like big data, hardware, and software. Let's say these are the three main reasons that, again, now we are dealing with this deep learning, and there have been successful applications of it in many fields. And therefore, also, if you look at it, yeah, there are different architectures that are developed during these past 10 years. Which they have yeah, different advantages compared to traditional ones. So in fact, there was a study showing that yeah, let's go deeper, because there was a competition for the ImageNet. ImageNet is a data set with a couple of millions of labeled image data, which have been as a benchmark for image classification. And there has been a study showing that indeed, if we go deeper, we would get better accuracy. So in 2010, I said 10, 11, it was shallow, and this is the error that you see, like 28.2. And as we go deeper, we have AlexNet in 2012 with 8 layers, and you see that the error is reducing. And we have VGGNet, which 19 layers, and then error again is decreasing. And we have GoogleNet, which 22 layers. Again, the error is decreasing. And finally, I mean, back that this was the study that was shown. Probably there are other recent ones. 152 layers of ResNet, and you see that that's the best result that they could get until 2015. So indeed, going deeper, because thanks to the fact that we have a lot of data and yeah, resources to train these networks, and there are different optimization routines that are developed, in fact, and also yeah, the activation functions changing from sigmoid or tangent hyperbolic to ReLU and other variants of ReLU. All these, the combinations helped to really go to really scale up these artificial neural networks and going to 152 layers and train them. So some of the aspects of regularization, as I mentioned before, so regularization is important for avoiding overfitting, and there are different techniques that have been used for regularization. One of them is data augmentation, or batch normalization, dropout, or imposing penalty on the weights of the network. So for data augmentation, we have horizontal flipping, or random crop sort scaling, or color jitter. So there are different techniques that can be used for augmenting your data and increasing the number of training samples that you have. And the other two frameworks that have been successful, at least for the deep learning part, is batch normalization, which, as you know, before feeding your data to neural networks, you normally normalize your data. And the idea of batch normalization is also the fact that you make the output of hidden layers also zero mean and unit variance, just as you do for the input data. So this will help for converging the network to a good solution at the end. And the other idea, which was has been discussed in deep learning community, is dropout. Dropout is a technique that you generate a mask, a random mask, and randomly you set some of these neurons during the forward pass. You set them to 0 during each iteration, and in that way you kind of learn which features are more important, and you regulate this network architecture. So if this is too much, then you regulate it by this way. And also it's like ensemble learning, has some connection to ensemble learning also. So this has been also shown to be very good for regularizing the network and always boosting the accuracy. Often boosting the accuracy of deep learning. And among other regularization techniques, as we discussed before, there are regularization. That means imposing penalties on the weights of the network. This could be L2, it could be L1, it could be L0, it could be other kind of norms that you can apply. But each one has its own advantage. So let's say for L1, if you want to have a sparsity, it's good to have L1 or L0 norm. But if you want to have like a uniform distribution over your weights, then it's good to have like a 2 norm. So we can now go towards convolutional neural networks, which is one of the successful architectures that have been used a lot for images and signals and many other data types. So instead of having just a neuron that is fully connected to the input, so if the input is an image, instead of having a neuron that is fully connected to the given image, we will have we will replace it with some other things that we will discuss. So if, let's say, if you consider this is the image of 200 by 200, and this neuron is connected to everything, is connected to all the pixels, then roughly you would get 2 billion parameters even for one layer. So what we can, this is huge. This would be very huge number of parameters to be trained. So therefore, we have to do something. So what is the idea? The idea is, what we could do, we could say, okay, we will have some filter size, like a patch, and we will connect only the patch of images to, not the whole image, but a patch of it to the neuron. So in this way, we could reduce from that 2 billion to 4 million parameters. But still, this is huge. And the fact that we did not consider that the statistics is similar at different locations. So even, if we now consider that the statistics is similar at different locations, so that means we could say these weights, I don't know if you will see my cursor or not, but these weights, they could be shared. So by sharing these weights, then we would reduce it to 100 parameters, because the patch size was 10 by 10. So now we came from 4 million to now 100 parameters, which is much easier to be trained. And this is the framework. This is the idea behind the CNN, that we shared the parameters across different locations. So we just have to slide this filter over the image, and we cover the image by these sliding filters. And the parameters of these always are the same. That means they are shared. So therefore, we have only 100 parameters to be trained. We could have other filters, not only one. We could, let's say, have 20 filters, and in that case, we would have 2,000 parameters to be trained. So then, yeah, the principle is the same. Still, we could apply gradient descent to learn these filters, because these filters are just the weights that we have to learn. But now we have, let's say, 2,000 parameters to learn. So this is another view that we can see. For instance, if there is an image of size 32 by 32 by 3, the 3 is like RGB, and the filter size is 5 by 5 by 3. Then if we slide this filter over the image, we would get a new activation map, which is of size 28 by 28 by 1. And if we have 6 filters, so then we would have 6 of these activation maps where we can stack them together, and then we would end up with the 28 by 28 by 6. So that means what we did here, well, we introduced these kernels or filters, which we convolve these filters. So that means slide it, like just product, element-wise production, multiplication. And then we end up with these activations. So what we did is we reduced the spatial dimension of the image from 32 by 32 now 28 by 28. But we increased the depth because it goes from 3 to 6, and this 6 is because we have 6 filters. So by having more filters, we are increasing the depth. But due to these convolution operations, yeah, the spatial dimension is reduced. There are some techniques that you can avoid reducing this, but yeah, for now, we will not discuss about that. So after obtaining these activation maps, then still we have to apply nonlinearity, because there is no nonlinearity involved in the process. It was just multiply the weights by that patch of the image and sum it up, and that will get that activation map. That will result in the activation map. So everything was linear so far. So we have to apply still this nonlinearity, which yeah, in the community we are applying the max this ReLU, which is the max of 0 and W transpose X. And by applying this element-wise for each pixel here, you would end up with a new activation map, which is now a nonlinear version. And then after that, we do a pooling layer, because yeah, there are several advantages. One of them could be, again, reducing the spatial dimension, and therefore reducing the number of parameters that can be learned, among other advantages that it has. So for a pooling layer, it could be, well, the principle is the following, that yeah, if you have 224 by 224 by 64, if you do pooling, that means you will end up with 112 by 64. So the depth would be the same, but the spatial resolution will reduce. And the way that it does it, so we have different poolings. Let's say we have max pooling, we have average pooling. You can also design your own pooling. But for max pooling, let's say this is the activation map that we have, and we want to do max pooling with a 2 by 2 filter and stride of 2. So therefore, if we just look at the first block, we take the max, we put it here 6. We go to the next block, and we take the max, and we put it there, and so on and so forth, until we cover the whole activation map. This will give us a new, let's say, representation of the original image, which is now ready in terms of spatial resolution is reduced, but in terms of depth is the same as before applying the max pooling. You could also apply the average pooling, so that means for every block we just take the average and just we replace it, and we get that average pooling. We could, well, in principle, we can repeat this process several times in order to have, let's say, deep convolutional neural networks. So that means we apply convolution and then apply ReLU, that means the nonlinear activation function. We get here, and we could apply the same thing, the same process again, and so on. This can lead us to a deep CNN framework. So what is known in this CNN architecture is the fact that the low-level features normally they are like Gabor feature, but they are learned from data in an end-to-end fashion. So in the past, from the computer vision community, in the computer vision community, they have been designing these features by hand or by, let's say, by different methods, but not in an end-to-end fashion. So they did not learn these things. But the beauty of this CNN is that, yeah, we can learn these features automatically in an end-to-end fashion just by means of input and output data. So the first level, the low-level features of Gabor, and then as we go deeper, Gabor-like feature, and as we go deeper, to the upper part, we see that more complex features are appearing. So these are some visualizations of the features, and there are different techniques for visualization, like deconf, or among other approaches, which one can look at. So therefore there is a hierarchical features that there is low-level features, mid-level features, and high-level features that are learned in an end-to-end fashion just by means of input and output data. So yeah, if we want to let's say summarize the whole process of these convolutional neural networks, so we have the image, we apply convolution, we apply ReLU, we repeat this process of, let's say 2-3 times, and then we apply pooling, and this would be like the first block, and then we go repeat this block again, second time, third time, and at the end we just concatenate or flatten all these filters that are obtained. And then we have the FC, which presents denotes the fully connected layer. So we have let's say two fully connected layers before the output. And then the task would be just to learn all these filters, and that means the weights of these filters. And that can be done exactly by the gradient descent that we have discussed in the past. So we should have a loss function, and we take the gradient of it, and we update the weights and biases of the network. And after doing that, when all the parameters, model parameters are learned, then one can really do out of sample extension, meaning that if the new image arrives, you just feed it to the network and pass it through these layers that the weights and biases are known, and then you get to the output, and that output hopefully it's a good one because you have trained your network carefully. So yeah, there are different CNN architectures. So one is Lenet. So it has this architecture. Yeah, the filter size is 5 by 5, stride 1. Average pooling, again 5 by 5, stride 1. Average pooling, and then fully connected layers. So that means flattening these things, flattening the last layer, and the two fully connected layers before the output. And you apply the softmax auto at the end. So this gives you the Lenet architecture. There was another one which we saw it at the earlier time also, that AlexNet, which which now we see that it has this architecture. So given the image, we have this convolution 11 by 11. So the filter size is now 11 by 11 and stride 4, and then max pooling and so on and so forth. So this process keeps going, and then at the end you have this fully connected dense layer, and then the softmax. So as we see that, yeah, the number of layers is increased from Lenet to AlexNet, and also we have another one called VGGNet, which again has the same architecture. I mean, in terms of having the main components of the architecture is CNN, but maybe yeah, the size of the filters and how many they are used, these are things that are different. But the main components are the same. That means they are applying CNN over image and get to the output. So there are many papers showing that CNN are many research papers that are showing that CNN are good for images. Indeed, it's good, and it has been started with images, but it can also be applied to other framework. Yeah, if you have signals and you want to yeah, analyze those, also that they can be applied. And yeah, recently what we did, we applied this for weather forecasting, weather element forecasting. So weather element forecasting can be reduced into a problem of learning a nonlinear map that maps the input to the target. and the input can be a regressor that we design, and that regressor is just the past values of the weather features. So if we concatenate all these weather features for the past, and then we obtain this regressor, and then we have a target that we want to estimate or predict, then this would be a machine learning problem that we have input output, and we want to learn it. We want to learn this underlying nonlinear function. So there would be several possibilities. One could apply SVM framework, but could apply neural networks approach. But here we wanted to explore the CNN framework. So what we did is we cast these regressors, which was a vector, into a tensorial format. So we have stations, weather stations, we have weather variables, and also the lags. So each input could be a tensor, and therefore this is really good for CNN. And then we are ready to apply CNN framework for this. And indeed, we can apply 2D CNN or 3D CNN for this task, as is shown here. For instance, here I'm applying the 2D CNN for this for the data in the data, and then we have a flattened layer and then fully connected layer corresponding to each output. Then we can train these networks, and then we can predict the target that we are interested in. I think in this case I was referring to temperature and also wind speed forecasting. We could also apply 3D CNN, meaning that we have this small kernel or filter that can be that will be slided over not only a station and lags, but also over weather elements. And this will result in applying 3D convolutional neural networks for this tensorial format, tensorial weather format. So here are the results of applying these techniques for wind speed prediction for in Denmark dataset for 6 hours and 12 hours prediction. And so here it shows the real prediction versus the model prediction. I mean, real measurements versus the model prediction. So as you see, the model is really following the trend. But as we go, as we want to estimate more steps ahead, let's say 12 hours ahead, the MAE or the metric that has been used is increased. And that's normal because the more steps you go for predicting that, the error would be more. Also we compared it with different models, 3D between 3D CNN, 2D CNN, 1D CNN, and also NARCS model and SDM. And for this data that was used, most of the time the 3D CNN was doing outperforming the others. And we also applied, did a p-value of a pairwise t-test, mean absolute error between these models. And here you see that there was a significant difference between the compared models. So the other framework that I would like to discuss is recurrent neural networks, where this is good for data sets that are in terms of sequence, like they are signals, sentences, and speech waveforms, among others, and that there is a time dependencies between signals, and that's very good if you want to apply RNN. So just a reminder, what is recurrent neural networks? So the difference between recurrent neural networks and normal neurons is that in recurrent neural networks or recurrent neural nets is each neuron has a feedback. So we have the input, we multiply by normally we multiply by weights, and then applying activation function, we go to output. But here there is a feedback internal state called SZS, where we multiply by some weight, which is called U, and then we sum it, will be added to the term that you know from the past, that W times the input plus U times the internal state, and then we apply the activation map. That would give us a new state, and then we can repeat this process for second time. As time goes, we can just apply this process. Time step 2, So we'll have S2 is equal to tonnage WX1 plus US1. So what is important here is that this W and U are shared. That means over time they don't change. So these are just fixed that we want to learn it. So if we, let's say, unfold this RNN across time, it would looks like this. That you have the input, you multiply by W, and then U times the S0. Then you are ready to go to S1, and then you have in the second time step, you apply the same process, and this keeps going till the end of the time interval that you are interested in. So if you look at the standard net, it looks like this, and in recurrent net we have again the feedback that we explained. Yeah, there is a feedback mechanism there that we just explained. So this is just for you to know that the difference between the two nets are the following. And mathematically, if we want to show it, it would be something like that, that there is this hidden states, sometimes referred to as S, sometimes it's denoted as H. But anyway, it's calculated by means of this formula here. And then if you want to go to the output, we just apply the weights on this hidden state, and we are ready to go to the output. So the three weights that should be learned or can be learned here are the weights that connects the hidden states, and the weights that connects the input to the hidden state, and the weights that connect the hidden state to the output. So these are the three weights that should be learned. If we unroll the RNN across time, the whole RNN across time, it looks like this. And so per step, one could have an output. And since we have an output, we could calculate the loss for each time step. And then the total loss would be the sum of all the losses at each step. And then once we have the loss, then we can just do the backpropagation. And we do the backward pass in order to learn all the parameters. Just simple example of this framework for RNN is, let's say, for character level prediction, where we have the vocabulary HELO. If we give this as input to RNN, of course we have to represent this. Let's say we use one hot encoder to encode this HELO to have this representation, and we feed it to the network, and then by means of this formula we could already apply, we could get all the hidden states, and then we can go to the output by means of the formula that you had seen in the past. And if we train this network and learn this WHY, WHH, and WXH, after learning that, then at the test time, we just give one character, and then we feed this character to the network, we go to the output, and we apply the softmax, we get the output, which is E. And then we can just feed this E again to the network and go to the output, and this can keep going till the end. And in fact, till the time that you would like to stop. So this is the framework of recurrent neural networks, and there are other applications of it for image captioning, semantic classification, machine translation, video classification, among others. So it's a very successful architecture that one can look at. The other framework is generative adversarial networks, where it has been used for learning the distribution of the data, the distribution that it generates the data. So this architecture is composed of two main architecture. One is generator, the other one is discriminator. The task of generator is to generate fake images and fool the discriminator or trick the discriminator. And the job of discriminator is to realize whether the given image is the real one or the fake one. The input to the discriminator is the real one or the fake. So these two components, they let's say they fight, and the generator wants to fool discriminator, but the task of discriminator is to not get fooled. So at the end, the parameters of these two let's say components or these architectures are learned by jointly by a min-max problem, min-max optimization problem, which is shown here. So the discriminator wants to maximize the objective. That means, such that the dx is close to 1 and dgz is close to 0, whereas the generator wants to minimize the objective such that dgz is close to 1. So that's the if we solve this min-max problem, at the end we will be able to generate fake images based on only random noise that is given to the network. So these are some fake images that have been generated by means of this framework, GANs, and yeah, really they look like real images. And these are like objects, and these are bedrooms, and there are other things that maybe you can look at on the internet, and you will see there are successful application of these GANs. Okay, so this was a general introduction of artificial neural networks and different architectures ranging from CNN, RNN, and GANs, where we started with perceptron, and then we started, we built upon it, and we covered these architectures. Now we can look at other frameworks which is based on kernel models. So one of the main difference between artificial neural networks and kernel models is the following. So in ANN, we have the input X, and we multiply it by W, which is the weight, and then we apply the activation function, the nonlinear activation function. So then the nonlinear activation function is applied on the weighted sum of the given input instance. So therefore, the model is nonlinear in W. In kernel-based model, what we do, we have the input, we map it to a new space by means of a feature map, let's say phi, and then we apply, then we multiply by a W, and then we go to the target. So that means, the model would be linear in W, and also it would be still capable of learning nonlinear decision boundaries. So that would these two, this is the main difference between, a simple component, a simple module of each framework. So more into kernel-based model. So if we have the input X, what we do is we apply a activation feature map phi, which normally is unknown. We apply this feature map. We map the input data to a high-dimensional space, which is called feature space. And then we multiply this feature space by these projected points by W, which is the weight. We go to the target space, and then there could be a set of constraints that we add to the optimization routine, and then we go to the output. And there are different frameworks, kernel-based framework. One is reproducing kernel hybrid space, RKHS, and there are Gaussian processes which are more probabilistic setting, and there are SVMs or least square version of it, which are more optimization setting. And in this talk, mostly I will talk about least square support vector machine, where in the primal it has been formulated as follows, where we have the objective function W transpose W and then E transpose E. We want to minimize that subject to this set of constraints that you see here. This is for regression, by the way, regression task. As you see this error, this is the one that we want to minimize because it's the difference between, it can be considered as the difference between the ground truth and the model prediction. And we have this W transpose W, which is a regularization term that is used to avoid overfitting. As I said in the last slide, this feature map phi is normally unknown, and we map this, feature, the input data to a high dimensional space, which is called feature space. Since we don't know this phi, we can't solve this problem in the primal. Therefore, we have to go to the dual. In SVM framework, that's the case. We have to go to the dual, and we should apply this KKT. We should get this Lagrangian, and then apply the KKT optimality conditions and eliminating the primal variables, then we can go to the dual. So that's the process. I didn't show it here, but that's the process that has to be done. And if we do that, then we go to the dual, which in this case, we will be solving a linear system of equation. So by solving a linear system of equation, which is shown here, we will get this alpha and bias. And based on these two, we can do the out-of-sample extension. So LSSVM model in the primal has this form. That means we represent the model in the primal in terms of feature map. And in the dual, it will have this form. Well, there is this alpha missing here. There should be alpha, in the summation. So if we have lots of data, that means the number of training samples is huge, then it's better to solve the problem in the primal. Because the size of this linear system of equation really depends on the number of training samples that we have, because this omega is a kernel matrix and it's of size n by n if we have n training samples. So if we have huge number of training samples, it's best that we don't go to the dual and we solve the problem in the primal. But the fact that we don't know the feature map, we can't solve the problem in the primal. So therefore, we have to somehow approximate this feature map. And therefore, there are different techniques. There have been different techniques to approximate this feature map and solve the problem in the primal. On the contrary, if the dimension of the data is huge, we have many variables, then it's best to go to the dual and solve the problem in the dual. So there are different techniques that we can solve the problem in the primal. Some of them are, one of them is called fixed size LSSVM, and this can be applied for regression classification, also for semi-supervised learning, where you have partially labeled data and also unlabeled data. This framework has been successfully applied, and for more details, you can refer to these two references here. So in the coming slides, I will just explain some of the methodologies that are used to approximate this feature map. So one of them is called Nistrom approximation of the feature map, where what we do. So suppose that we have n training samples where n is huge. Then what we do in Nistrom approximation, we subsample this n. We work with some prototype vectors. We select m training samples from this pool of n samples, and then we would build a kernel matrix only based on these small m samples that we selected, and then we do the eigendecomposition of this kernel matrix. We get the eigenvalues and eigenvectors, and based on that, we can, based on this formula that you see here, using this formula that you see here, we can approximate the ith component of the m-dimensional feature map, where this m is that m that we fixed. So we first select m points from the n points that we had, and that will be the dimension of the feature map that we will have at the end. So by using this formula, one can compute the ith component of this fixed size or m-dimensional feature map. And if we do that for all the elements, with all the m elements of this feature map, then we have this explicit feature map already, and we can use it in the primal to solve the problem in the primal. The other framework is introduced by Mangasarian in the SVM framework, which instead of using a square matrix, you will be using a rectangular matrix, and that's also an option that one can use. And the third framework is random Fourier features, which is introduced by Rahimi and Benjamin Brecht and the rest. So random Fourier features correspond to the kernel function K. It can be obtained by means of this formula, where the ith component is obtained by means of this cosine of this product, where x is your input and z is sampled from a distribution P. And it's shown that for RBF kernel, they can be drawn from a normal distribution with zero mean and standard deviation. So, well, anyway, if one approximate the feature map by means of any methods that are available, then we can have this m-dimensional approximation of the feature map, Therefore, we can rewrite the primal optimization of the least square support vector machine, which was shown here. We could rewrite this as the following optimization by eliminating the constraint. So this would be unconstrained optimization problem where we can now solve it in the primal as it is now. And the solution is shown that it can be obtained by means of solving just this linear system of equation. So that means here we have to take the inverse of a matrix of size m plus 1. By the way, this 1 is because there is a bias there. And we know that m is small because we chose that m. So therefore, the inverse of this matrix is doable and it can be computed easily. And based on that, we get this W, the weights and bias. And once we have these two vectors, the vector W and the bias there, then we can do the out of sample extension by means of this formula. So that means if the new test points arrive, we just map it using this explicit feature map that we know, and then multiply by the weights and the added bias. We go to the score variables, and then we can decide about if it is a classification or regression. We can decide about that. So if we look at it, if there is implicit feature mapping involved in the kernel-based model, so that means the projection space corresponds to a hidden layer in a neural network with infinite number of neurons. So that's also a connection between kernel models and artificial neural networks. So if you're talking about support vector machines or least square population or any kernel models that they involve, there is a feature map involved, which is implicit feature map. Then the projection space corresponds to the hidden layer in a neural network with infinite number of neurons. And of course, if we use the explicit feature map, the dimension of this explicit feature map also can be correspond to the number of hidden units in a hidden layer of a neural network architecture. So there is this correspondence between the two framework. One can view it in this slide. So we have also developed a hybrid model based on the combination of neural networks and kernel models. So it has this architecture where you have the input. There is a linear transformation first, and then we apply this explicit feature map that can be obtained by one of the methods that we discussed. And then we go to the fully connected layer before the softmax, and then we apply the softmax, and then we have the loss, and then we optimize the weights and biases based on gradient descent, and then the model is ready to be used. So this is the model that we have introduced in 2018, I guess. It's called Deep Hybrid Neural Kernel Network Architecture, and this is the optimization that has to be solved. So here we are dealing with matrices. That's why we just call it trace of this W1 transpose. This would be the regularization term. We have two regularization terms and the loss function. And for the loss, we are using cross entropy loss. And then we use the gradient descent to optimize the weights. And once these are obtained, we can do the out of sample extension easily. And by means of this formula that you see, we can obtain the score for the new test points. And then we could apply the argmax on this and get the real output. I mean, the predicted output predictions. If we compare these models with other models, that means shallow LSSVM, primal and dual, both primal and dual, we see that most of the time, in fact, all the time, is outperforming the other two frameworks. So the new framework is outperforming the other two, and this could be thanks to the fact that it's now deeper. It has more layers. And there is this linear transformation that the traditional LSSVM framework or SVM framework, they didn't have it. So that's the result of this model. The other framework that has been recently introduced is deep narrow kernel blocks. So for that, we have to look at the activation function more carefully. So before the activation function applies, if this is the neurons before activation function in normal neural networks architecture, let's say we have ReLU, which is the case. Most of the architectures now they are using ReLU. So you see that this is applied element-wise to each neuron, and then you get the nonlinear version of each neuron. But what can also be done is that we apply the feature map on this neuron before activation function, and then this would be a nonlinearity that is involved in the neural network. So that means we are imposing a feature map instead of just a ReLU there. So this would be again a connection between neural networks and kernel-based model. So we have tried this framework and we developed it further. We tried something which we call max out kernel blocks, which is the stack of different blocks, several blocks, and just looking at the first block. So we have the input, we have multiple linear transformation of the input. So we first have multiple linear transformation of the input, and then we take the max out of this, which is called max out. Also, there is this framework of max out in neural networks, which is kind of nonlinearity, which is imposing a nonlinearity there. And then after that, we can apply the explicit feature map to go to the first hidden, let's say hidden layer, and which we call it edge. And this can continue by adding the next max out kernel block, and so on and so forth till the end. So this architecture, we call it max out kernel blocks, and these are the formula that are used for each block. The other framework that can be used is convolutional kernel block, where first the input is mapped linearly to multiple linear transformation, and then we concatenate them, and then we apply a convolutional operation, but with filtered one by one, because we would like to reduce the dimension or the depth. And after that, we apply the explicit feature map. We go to the first layer, and this constructs already the first convolution kernel block. And then we can, once we have this block, we can repeat this block several times, and we can stack them in order to have a deeper network. So we have done that. This is the second architecture that you see here. And if you, after training these networks, if I visualize the weights of the first block, this would be the weights of the first block before the activation function. So that would be something that we see. There is a kind of a sparsity involved. But the second row corresponds to the weights after activation function in the second block, I guess. Then that you see that because there was activation function involved, this nonlinear activation function involved, therefore the sparsity is lost. So this is just to show that what the network is actually learning. It makes sense for the network just before activation function to have this kind of behavior, and then after that this kind of behavior. So here we have compared these new architectures with other existing architectures, and we see that instead for several data sets from UCI machine repository, and we see that most of the time or often the max out outperforms the other models. Also, it has been used in connection with CNN on three different data sets: MNIST image data set, MNIST CFAR10 and CFAR100. And there has been, we have compared with other models, and we see that sometimes it outperforms, and sometimes they are, either they are comparable or outperforms the other ones. So it's comparable to the existing architecture that even the neural networks architecture that you see in the literature. And this is some plots regarding the training of the networks that has been discussed. So here we have been analyzing what would be the effect of having let's say 1 block or 2 block or 3 blocks or 4 blocks. That means as we go deeper, what will happen. So in general, as we go deeper, as can be seen here, the network converge faster. But at some point, as we go deeper, that means the number of model parameters also increases, and therefore the problem of overfitting can also occur. And therefore, in general, it's good to have this kind of numbers of blocks as a hyperparameter that can be tuned. Validation, cross-validation, by means of cross-validation to have the optimal number of blocks. But this is just to show that this is the behavior of the network when you have one block, when you have 2 blocks, or 3 blocks, or 4 blocks. And within each block, there would be several multiple linear transformation, which we have also tried it, and I think it's been shown also in this video. So the other aspects that can be seen is, so if we use the t-SNE projections on the test data, we see that as the data flows through the network, the beginning doesn't have any structure, but as we go deeper, we see that the data forms a kind of separable clusters, or separate clusters corresponding to each classes. So this is also nice to see that indeed the network is converging to something that is useful and meaningful. So the last part of my talk would be about domain adaptation problem and covering some of the models that we have been trying for dealing with this task. So the common assumption of ML algorithms, machine learning algorithm, is that both training and test data exhibit the same distribution, and we are dealing with fully labeled training data, and there are same feature domains, and also dealing with the stationary data set. But in reality, collecting training data in different domains is costly, and statistical properties evolve in time. And also, for sure, the performance significantly drops when the model is presented with new test data that is different from the training data. That means this distribution is different from training data. So the aim of transfer learning or this domain adaptation is to transfer the knowledge or adapt it to a new target domain. It could be different features. It could be different dimensions. There are several possibilities that can be considered. One of the example is like you train your network with source domain on which is like on syntactic data, and then you apply it on real data for the target domain. And it has many applications for a spam filtering problem, cross-domain action recognition, document classification, speech recognition, name it. There are several applications of this domain adaptation problem. So there are different learning types that one can consider is unsupervised domain adaptation, supervised one, and semi-supervised one. And there would be different type of domains that one can also consider. It could be homogeneous domain, it could be heterogeneous domain. And normally heterogeneous domain are more difficult than the homogeneous one. And also there would be different methodologies that one can try. Would be shallow-based model or models with deep architecture. So among shallow-based models, the successful shallow-based models, one can summarize it in the following: that there are dynamic ensemble, there are sample rebaiting, and there are feature transformation. So in dynamic ensemble, normally these models they combine a set of base components through a decision fusion rules. And in sample rebaiting, we will normally they will assign sample dependent weights to the training data in order to minimize the discrepancy between the distribution of the source and target domain. And in feature transformation, they would learn a domain invariant feature. So they would project these two source and target domain to a new domain. So that would be a feature transformation. So for instance, one of the successful framework in this domain adaptation is this paper, that's domain adaptation weight transfer component analysis, which has been cited a lot. And the aim of this work was learning a latent representation for both domains that present the data configuration of the two domains after transformation. And this is done by learning a feature map, a nonlinear transformation file, which, at the end, the distribution after the transformation is the same. and they use this distance, which is the square distance between the empirical means of the two domains after the projection. This distance is used as, let's say, cost function for them. And the other framework is covariate shift adaptation, where within the expected risk minimization or framework, normally we will use this loss function to, normally we use this loss function, we try to minimize this loss function, where here there is a loss and this is the joint probability distribution. But in case that the joint distribution of the test and the target are not the same, then yeah, this framework will not work well. That's why people, I mean, researchers, they have tried to adapt this risk minimization framework by assigning some weights to the loss function, and that is based on this yeah, ratio that you see. Density ratio between which is obtained based on the distribution of the test and target domain, and by this they will solve a new framework, a new minimization problem, where the loss is weighted now, and by doing that they will try to minimize this yeah, the distribution discrepancy that exists between the training and test data, or sourced on target data points. So in this framework, there could be also side information, several side information available in the form of correspondence instances. That could be, for example, pair instances. You could consider that a person is doing the same action, but in different domains, different views. And so that could be the correspondence instances that exist in the dataset that can be exploited. So in this work, what we did was to consider different scenarios for having unlabeled pair data. This pair data means, yes, having this correspondence, unlabeled ones, unlabeled semi-paired data, and the last scenario is unlabeled plus labeled semi-paired data. So this last one is covering the maybe the most general scenario that one can consider in this yeah, in this scenario, in this case. So we develop models based on canonical correlation analysis to solve this domain adaptation problem. So in general, what is canonical correlation analysis? Is the objective is to find a basis vector, two basis vector W1 and W2, such that when you project this to these projected variables are maximally correlated, and therefore with this, it has been shown that if you solve this maximization problem, you would end up with this optimal W1 and W2. But CCA measures the linear relationship, so that's why in the literature also they have been trying to use the nonlinear CCA or kernel CCA version of it, and so in particular in the book of John Sorkins, we see that we see a LSSVM formulation to kernel CCA, which is in the primal is formulated as this, where the first one is the objective function that has to be maximized subject to this set of constraints, two set of constraints, and again, as before, if we cannot solve the problem in the primal, we have to go to the dual, and if we solve it in the dual, it would be an eigenvalue problem in this case that has to be solved, and based on that one can get yeah, the alpha and beta, and based on that one can compute the components. So if we consider the last scenario that we discussed, unlabeled plus partially labeled paired data, so we call that framework regularized semi-paired KCCA. KCCA is because the core model is KCCA, but we add something to it, into the objective function of it, and therefore is called regularized semi-paired KCCA. So assuming that we have two data sets, one for source and one for target, and we are dealing with paired, labeled, unlabeled data, as well as unpaired, unlabeled data, unpaired, labeled data for the source domain and target domain. Also, we have paired and unpaired, both labeled and unlabeled data points. So the setup is the following, that only a small number of paired labeled data points from both domains are available. Sort data set is equipped with additional unpaired labeled instances during training. And we assume that there are Q classes And the label indicator matrix Y1 for the source domain is denoted by this, where is 1 if the I point belongs to the J class, and otherwise is -1. And the same in label indicator matrix Y2 is constructed for the target domain. So these are the setup, and this is the primal optimization problem for this domain adaptation task that we have. So there are many terms here that yeah, I'm not going through all of the terms, but yeah, it's, again, this is based on kernel CCA, and we have added yeah, this term which has V1 and V2, as well as these two terms. So there will be three new regularization terms that are added to the framework. And we have this set of constraints that we project the data points of source and target domain to a new space. And we learn this domain invariant features in that space. So we cannot solve this problem in the primal again, due to the fact that we have this file, which is again this unknown feature map, which is unknown, I mean, which we don't know. Therefore, we have to apply this QKT optimality conditions and go to the dual. And in the dual, we see that now we have to solve a linear system of equations. So by adding this new set of regularization terms that are added in the objective function of Lisa Square's kernel CCA framework, we see that we reduce the eigenvalue problem to a linear system of equation. So that's easier. So we can solve this linear system of equation easily. And once this is solved, then we obtain alpha and beta, and then we can apply this formula in order to obtain the score variables for both source and target data points. So that means this ZEL and ZRL would be the new projections of the data points of source and target, which are domain. So these are they are in common space, let's say. So this the elements that are used in the first formula, like omega c and omega c2, these are called centered kernel matrix, calculated as follows, and the centering matrix MC that is used here also has this form that can be used. So as an example, if we have these two moons problem, where at the top left we see the two moon problem, two moon data set, and it's rotated and shifted towards down. So if you apply any classifier for the first two moon that you see in the top left, you apply your classifier, your favorite classifier, and you learn all the parameters of that classifier, and then you give this new two moon data set that is in the right bottom corner to your classifier will fail, because the new data set is rotated, and that means the distribution is a bit changed. So it will fail. But with this framework that we introduced, we can project all these source and target to a new space, and then in that new space, all of them are aligned, the projected variables are aligned, and therefore easily one can learn the classifier in that space. So that's the advantage of this framework that we introduced. So so in summary, type of instances that can be used by the proposed models are paired unlabeled, unpaired unlabeled, paired labeled, unpaired labeled. So this regularized semi-paired cases here that we introduced, it can use all these scenarios. So in any other in other fields that this type of data set fit, definitely these methodologies can be applied. And also I should mention that for larger scale data, that means if you have a huge amount of training samples, still we can also apply the explicit feature map and solve the problem in the primal. And it has been discussed in the paper as well. So there is this possibility that it can be applied both in it can be solved both in primal and dual. Other framework deep learning based approaches that can be applied in this scenario could be extracting features by means of deep CNN models and use them in shallow DA methods. fine-tuning the pre-trained networks using the source domain, and developing deep architecture designed specifically for domain adaptation. So one of them is extracting common latent representation by means of a stack denoising autoencoder, and the other one is called marginalized stack denoising autoencoder, where the framework is, they don't use gradient descent to solve the problem. There is a closed form solution for their optimization problem. And the other one is fine tuning. That means you use the pre-trained network, and then you fine tune your network using your target data set that you have. So the last work that I want to introduce is called cross-domain neural kernel networks. So it's used for a domain adaptation problem in a semi-supervised fashion. So we have two streams. Probably you recall this framework, the first one. Here we have two streams corresponding to the source and target, and we impose the regularization term in the intermediate layer for the paired data samples that we have. So the objective function would consist of the loss function for the source, loss function for the target, and this regularization term that you see that minimizes the cosine distance, that aims at minimizing the cosine distance between the intermediate projections of the data. And this is why, because this paired these data sets are paired, and therefore we assume that this projection should also be similar to each other. So by imposing this, when we minimize this, so this is for like multi-feature data set that you see we have. I'm just plotting here. The different loss corresponding to cosine loss, source loss, and target loss, and you see all of them they are converging. And here we just apply this for X mass data set, and we compared it with other framework, the previous method that we were working on, and also the marginalized stack autoencoder, which is kind of deep learning, and also this FA, which is known in this domain adaptation community. And most of the time, the new framework was performing better than or outperforming the other. Okay, so thank you very much for listening. I hope it was useful, and if there are questions, I would be happy to answer.
Okay, many thanks for the talk. So let's wait for maybe some question, but may I ask you a question by myself?
Yeah, sure.
Just from point of view of student, when I was a student, my teacher always told me that, you can't remember all formulas or everything during long talk, okay? We even don't have a time to read this formula, okay?
Yeah.
But when I leave any lecture, this one, I want to have 3 sentences in my brain, what I learned something new and what is the main point. So can you give us 3-4 sentences what I have to keep in my mind after listening to your lecture?
I see. Well, that's a very difficult question, but I will try to.
I know, but I don't have infinite memory, and definitely I don't remember even one formula from your talk. So I will be happy to have some summary.
Definitely. So the overall talk was, the first part was about introduction to neural networks. If someone doesn't know it, so probably now they will know something about it. And the second part was about the combination of, first introduction to a least squares super vector machine framework, and then we introduced some new frameworks which is based on deep neural kernel-based approach, which is new and is a combination of neural networks and kernel-based models. So that means we are using new activation function, let's say, which is based on kernel models and feature maps, explicit ones, and we also saw several methodologies in that regard. One was neural kernel blocks, the other one was the last one that I used for domain adaptation. And some other messages, take-home messages, would be the connection that exists between kernel models and neural networks.
Okay, so I will specify my question. My feeling is that when you use kernel and neuron, you see, deep neural net is just sequence of linear transformation and pointwise nonlinearity.
Yes.
So you introduce in some place, like, let's have more complicated nonlinear transformations than just pointwise.
Yes,
So
that's
why don't just call this neural net with a nonlinear feature extraction? Why use word kernel? Because I don't see any need from kernel methods to involve this. You just add additional layer of nonlinear transformation.
no, but that nonlinear activation function, nonlinear mapping, is obtained by means of a feature map that are used in kernel models. So the one that I introduced, like Nistrom approximation of the kernel of the feature map, or
Because this was misleading me, because when you combine something, it means that you enhance something together. But it wasn't really kernel method. You just pick some maps which show that in some problem are useful and just add as an additional feature extraction. So there is no really connection with the so-called kernel method. You don't learn new kernel, nothing. You just take some nonlinearity. Am I right? No, I just want to clarify for myself.
Well, in this, I mean, for now, we don't learn the kernel. The kernels are there because we just use these approximation techniques that are used in kernel models and approximate the feature map, and we used it in the neural networks approach, right?
Oh, so may I just summarize?
But it could be that also we learn this kernel automatically in an end-to-end fashion, but this hasn't been done yet. But indeed, this is like a starting point for some other things that can be done. Indeed.
Okay, sir. Maybe we'll discuss later.
Yeah.
Any more questions? I don't see any question on the chat. So, do you have any more questions? Okay, if this is not the case, so once again, many thanks. It was a pleasure having you here.
Yeah, thank you.
And talk to you later in another room.
Sure.
Okay, thanks.
Yeah, thank you.
Bye-bye.
Bye-bye. So I guess we can leave now.
I think if Eugene want to say something, keep the floor.
Okay, so thank you for attending this tutorial day. I think we had quite good 4 tutorials, right? And we are also already quite exhaustive, I would say. So tomorrow we start with the conference itself, and it will start at 9 o'clock. So then we'll see each other again. So thank you again.
Your time.
Yeah, 9 o'clock. Sorry, yeah, Central European time.
8 o'clock UK time.
Just a second to be totally sure. Yeah, it will be 9 o'clock Central European time. It means 8 o'clock Greenwich time. So, okay.
Eugene, let me say that the live streaming was successful. I will give you some numbers, and so that tomorrow you can say something, because number are growing. And yeah, I'm totally happy about this.
Okay, but I still think that it's a good idea that you present tomorrow again the rules for the Zoom sessions, because there will be at least 15 people that will be newcomers for the only just for the symposium. Right?
Yeah,
so
yeah, sure. But
introduction, and then you can actually say something about the attendance. All right.
Yeah, but just to be sure, no more YouTube starting from tomorrow. Yeah.
Yeah, for sure. Yeah. Okay. Thank you very much. And then see you tomorrow.
See you tomorrow.
See you tomorrow.
Bye-bye.
Bye-bye.
Bye.